Mostly we do not write left or because it is mostly clear from the context, but I have just written it in the bracket. Then a module homomorphism, f from m to n satisfies. I'm going to write the conditions which are to be satisfied. First condition is effect of f on sum of x and y is equal to sum of fx and fy. This is same thing as you already know. F preserves addition. You know this thing from your concept of groups. And f of a composed with x, in fact, because a is element of the ring, x is element of m. So a composed with x, ax, and effect of f upon ax is equal to a composed with fx. This is called linearity, in fact, and this is for all a belonging to R and xy belonging to M. So this is the definition of module homomorphism. So having defined what a module is and what a module homomorphism is, we are very well aware of the category or mod, whose objects are left are modules and morphisms are module homomorphisms. The category or mod has left or modules as objects and module homomorphisms as maps or arrows. So this is the structure of or mod, category of left or modules. Now we come to construction of product of two or modules in the category or mod. So product of two left or modules in the category of left or modules, we have denoted it by or mod. So this is what we are going to discuss. So let M and N be left or modules M and N be left or modules then we know that what I'm going to discuss is, you know it very well. This is the module structure of M cross N, and it is defined point wise. You will see it is very simple. Then let me write it. We know that M cross N, this just Cartesian product of M and N, is also left OR module under component wise operations, and you know this phrase very well, under component wise operations. And what does this mean? It will be very clear very soon. You already know that. That is, first of all, let's see what M cross N is. You know that this is just the Cartesian product of M and N, that is set of order pairs XY, such that X belongs to M and Y belongs to N. So this is M cross N, and now first of all we are going to define addition on M cross N, and that is, if we are given two elements x1 y1 and x2 y2 of M cross N, we define their addition component wise. That is, first component added with first component and second component added with second component. And this is for all x1 y1 and x2 y2 belonging to M cross N. So this is addition defined on M cross N. This particular order pair 0, 0, which belongs to M cross N, is additive identity. You can see it very easily. This is additive identity in M cross N. And then thirdly, if you take any element X cross any element order pair XY belonging to M cross N, then this has minus X minus Y, which again belongs to M cross N as additive inverse. In fact, what I am saying is that minus X minus Y ordered pair is inverse of additive inverse of XY ordered pair, because X added with minus X will be 0, Y added with minus Y will be equal to 0. So this is additive inverse of XY. And the remaining properties, that is associativity and commutativity, is very clear. In fact, it gets inherited from M and N. Commutativity and associativity of this particular operation, which is component wise, is obvious. This is very clear. You can check it on your own. Is obvious. Therefore, M cross N is an abelian group. So therefore, M cross N is an abelian group. Under addition. So first condition to be a module, a left arm module, is that the set has to be an abelian group under addition. So we have established that M cross N is an abelian group under addition. So M cross N is an abelian group under addition. Now we come to scalar multiplication. Scalar multiplication in M cross N. So scalar multiplication in M cross N is given by this again component wise is given by if xy is an element of M cross N and A is an element of the ring, then their composition is defined as AX comma AY. This again component wise is for all elements of the ring and all elements of M cross N. So this is the way we define scalar multiplication. And other conditions for M cross N being a left arm module are satisfied, and you can verify it on your own. The conditions for M cross N to be a left arm module those are 4 conditions we have already written, can be verified very easily. So what we have established is that M cross N, therefore M cross N is left arm module under operations defined above. So in brief, this was left arm module structure of M cross N. Now we will prove that this particular left arm module M cross N is product in the category of left arm modules. So we shall prove that M cross N is product of M and N in the category or mode. So this is what we are going to do. So let's come to proof. And by now you understand what we mean by product. That is, we must have two very special morphisms called projections and a universal property we have discussed in the case of sets. So first we note that projections are given by, in order to prove that M cross N is product, we have to define projections. Projections are given by so we have M cross N. This is the module we have defined above, and the projection, first projection P1 from M cross N to M, and second projection P2 from M cross N to N. These are given by, if xy is an element of M cross N, then under projection P1 this will go to X, and under projection P2 this will go to Y. And this is what we are saying, that is effect of first projection on XY is equal to X, and effect of second projection on XY is equal to Y. And this is for all XY belonging to M cross N. So these are the projections. To see that these projections are module homomorphisms, it is very easy, and if you like you can do it on your own. You can easily see that P1 and P2 are module homomorphisms. So having discussed the projections, now we come to the universal property. So we are going to take a diagram as we have done in the case of sets, and then we are going to establish a unique module homomorphism so that a particular diagram commutes. So for that purpose, let C to N and C to M, this morphism, let's write it as phi and let's write it as psi. So let this be a diagram in the category of left OR modules. Let this be a diagram in the category of left OR modules. This means that C is a left OR module and there are morphisms with domain C to M and to N. We denote these morphisms, module homomorphism, by phi and psi. So let this be a diagram in the category of left OR modules. Now we have to define a morphism from C to M cross N. So let us draw the diagram. Let us draw the diagram for better understanding, in fact, for better understanding. So we have left OR modules M and N, and we have noted that M cross N is also a left OR module, and this left OR module is equipped with projections P1 from M cross N to M and P2 from M cross N to N. So this is what we have already discussed. Now we are considering a diagram. C is a left OR module which is equipped with two morphisms. From C to M we denoted it by phi, and from C to N we have denoted it by psi. So this is equipped with these two module homomorphisms. We have to establish, or we have to prove, existence of a unique module homomorphism from C to M cross N. Let's write it as F, so that this particular diagram commutes. So we have to define F so that P1 composed with F is equal to phi, and P2 composed with F is equal to psi. So let's see what this definition is going to be. So we define F as follows. So domain of F is C. So we take an element of C, let's write it as small c, and effect of F upon this small c is going to be, result should be an element of M cross N, that will be an ordered pair. So effect of F upon C is going to be, what we are going to do is that we are going to apply phi on C, that will be an element of M. So phi C, this is an element of M. Next we are going to apply psi on C, this will be an element of N, psi C. Now this is element of M, this is element of N, so this is going to be element of M cross N. So this is the way we have defined F, and it is very easy to see that F is a module homomorphism. It can be verified that F is module homomorphism. So this is the way we have defined F. Now we have to prove that the diagram commutes, and then we will come to uniqueness. Just note that we have done commutativity. It is the same as we have done in case of sets. So it can be easily seen that as we have done in the category set, as we have done for the category of set where we considered Cartesian product of two sets. So it can be easily seen that composition of P1 with F is equal to phi, and composition of P2 with F is equal to psi. This is exactly the same as we have done for the case of Cartesian product. Uniqueness is again same, but let me do that just to make you understand these things better. So for uniqueness, suppose that this is for uniqueness of F. So suppose that there is we have to prove uniqueness of F. So we are going to consider another module homomorphism from C to M cross N so that this diagram commutes, and we will prove that that module homomorphism turns to be F again. So suppose that there is a module homomorphism. From C to M cross N. From C to M cross N, and we call it G, such that this particular diagram which I'm going to draw, this is M cross N, we have projections P1 and P2, and we have maps from C to M, which is phi, and C to N, which is psi, and we have supposed that there is a module homomorphism from C to M cross N such that this diagram commutes. So this diagram commutes means that is P1 composed with G, P1 composed with G is equal to phi, and P2 composed with G is equal to psi. So this is what commutativity of diagram means, and therefore effect of P1 composed with G on any element of this module C is same as effect of phi on C, and effect of P2 composed with G on C is equal to effect of psi on C, and therefore effect of projection P1 on GC is equal to phi C, and effect of projection P2 on GC is equal to psi C. And you can see that this is possible only if this is possible. Let's write it for all C belonging to C. So this is possible only if GC is equal to phi C and psi C order pair. Because GC is an element of M cross N, and P1 is going to take GC to phi C. The P1 is the first projection. So first element of GC is going to be phi C, and second element of GC has to be psi C, so that first projection becomes phi C and second projection becomes psi C. And you know that phi C psi C order pair is exactly what FC is, and therefore G and F are equal, and therefore F is unique. We have established every aspect, so therefore M cross N is product of modules M and N in the category of left OR modules. Now, having considered two examples, one is products in the category of sets, and secondly products in the category of left OR modules, we are in a position to give formal definition of product. So let's have formal definition. So let C be a category. We denoted category by C and then slight curve at the top top just to distinguish it from the letter C. So let C be a category. If you like, you can take some other symbol. Anyway, so let C be a category. Then the product A cross B of two objects A and B of C B of category C is an object of C such that object of category C such that so first condition is A cross B. This is the symbol for product of A and B, not A cross C. We just A cross B means Cartesian product of A and B, but in general category we also use the same symbol A and then we put cross and then B. Anyway, such that so this particular object is product in the category C such that this particular object we have denoted by this symbol is equipped with two maps is equipped with two maps or two arrows or two morphisms is equipped with two maps. One is from A cross B to A, we denote it by P1, and the second is from A cross B to B, we denote it by P2. These maps are called projections. And secondly, such that for any diagram C to A and C to B, these are maps phi and psi, such that for any diagram in the category C, there exists a unique map from C to A cross B. A cross B, in fact, product of A and B. From C to A cross B, let's denote it by F, such that the following diagram commutes. And you understand this diagram very well now. This diagram is, this is the product and this is the first projection and this is the second projection, and from C we have two maps, phi from C to A and psi from C to B, and there has to be a unique morphism, unique map from C to A cross B F. And this diagram commutes means that P1 composed with F is equal to phi and P2 composed with F is equal to psi. So this is the definition of product of two objects in a category C.